Yep, I'm here. All good. I'm fine.
Better late than never. I want to start with a question that we had to hold over from last week. His name is Devon. He's 10 years old, and we promised his dad that we will start the show with this question. And Devon, who is 10 years old, asks, Why is it that when we go to the bathroom for a number two, we sometimes get a big shiver and sometimes even get goosebumps? This even happens in summer, so it can't be from the cold, asked 10-year-old Devon. Chris?
This is a common phenomenon, Devon. Welcome to the club. Many of us do it, but most of us just don't talk about it because we tend to not talk about bodily functions. But it's common. And it's not just associated with going to the number two. You also find some people will do this when they have a wee. And so why is that? And the answer is that when you have a number two or a number one, you are using your autonomic nervous system. This is the automatic part of the nervous system that controls things subconsciously that you don't have to worry about. So all the things that are to do with, say, relaxing various what are called sphincters, muscles that hold things closed, if you get what I mean, you need to open those up. You need to tell the muscles in your bladder, for example, to start contracting, to squeeze out wee, or the muscles in the rectum to start expelling feces. All of this is not under conscious control. It's under the control of this automatic part of your nervous system. And when it does that, when it disengages certain parts of the nervous system and engages other parts, there's an overlap or a spillover into the adjacent sort of control circuits that are also to do with other processes that we can't control. Shivering is one of them. And so it's a sign that you're activating the sympathetic and parasympathetic parts of your nervous system. And it just happens because of that spillover from one part of the circuit into the other, just temporarily, while you are doing this. And as I say, it is very common. Most people say that they get these sensations.
Excellent. Devon is in school, but his dad said that he would be recording this answer. So I hope, Devon, 10 years old, I hope you've appreciated the answer. Ellie is asking you on the WhatsApp line, could the naked scientist tell us in layman's terms how carbon dating is done? Thank you so much, Ellie.
Morning, Ellie. Carbon dating was the insight of a guy called Willard Libby. And what he realised is that carbon has two flavours that are common on Earth. One flavour or isotope is called carbon-12. That's the most common and it's completely stable. When something's in the form carbon-12, it doesn't change from carbon-12. There's another form of carbon, which is called carbon-14. This is radioactive. And so it decays or changes from carbon-14 into carbon-12 over time. And the half-life with which it does that is about 6,000 years. So in other words, after 6,000 years, the amount of carbon-14 you start with has halved. And so you end up with half as much on average as you started with. And after another 6,000 years, it halves again. And that's called radioactive decay. And it follows that predictable formula of these half-lives, with the amount halving each time with every half-life. That's why they're called half-lives. In the atmosphere, there's a roughly constant amount of carbon-14, because high up in the atmosphere, where the planet is being bombarded with radiation from space, other components of the atmosphere, like nitrogen, are being smashed into by radiation, and this turns some of these other elements into carbon-14. So you can assume the carbon-14 in the atmosphere is roughly constant. This means that trees and plants, which are green and photosynthesizing and using carbon dioxide, are incorporating a known amount of carbon-14 into themselves all the time while they're alive. But the minute they die or are eaten by, say, us or an animal, the amount of carbon-14 that's in that thing starts to fall because no more carbon-14 is coming in the food, but there is nevertheless loss of carbon-14 as it turns into carbon-12. So if you dig up something that's been in the ground for a while, the last time it was exchanging carbon-14 with the air must have been when it was alive. And therefore, if you measure how much carbon-14 is in it now, you can work out how much different there is from what it should be compared to when it started, i.e. what was in the atmosphere, and that tells you how many half-lives must have passed for it to have decayed down to that amount, and that tells you, if you times it by about 6,000, how long ago it was that the thing was alive and breathing and eating like we are today. And that's how you backdate. You can't go back forever, though, because once you get back to about 60,000, 70,000 years, you really are pushing the limits of the detectability and the reliability. You're getting a lot of statistical noise in there. And so therefore you can't go back beyond a threshold of about that far.
So the oldest thing that we've ever carbon dated would be at maximum 80,000 years old.
It would be even younger than that. Probably 60,000 or so is when it's reliable. So then you're going to ask me the question, Lester, well, what about other things? How do we go back further? And the answer is that the same trick works for other radioactive elements. So if you wanted to date the Earth, I don't mean take it out for a dinner. I mean as in if you wanted to work out how old bits of the Earth are, then you can use different isotopes, and geologists will be very familiar with something called the uranium-lead time. So if you find a rock, you can look at the uranium atoms that are in there, and we know that when the planet was forming, there's a certain amount of uranium there. As uranium decays radioactively and spits out various other species, it turns into lead. So if you work out the ratio of uranium to lead, it tells you how old that particular bit of the Earth is. And so we can use this to date asteroids, things coming in from space, and the Earth itself. And so it's usable because the half-life, the rate at which uranium turns into lead, is not measured in a few thousand years, it's measured in millions of years. And that's why it's much more appropriate for long-term timescales.
So the Earth, am I correct, about 5 billion years old?
We agree the Earth is about 4.5 billion years old, and the solar system as a whole probably 5 to 5.5 billion. Why the difference? Because it takes time for a solar system to be born. A big cloud of gas and dust falls together and begins to ignite a star. That star is gravitationally active and pulls other material and debris into a disk around the star. That's called a protoplanetary disk. And under the influence of gravity, bigger bodies, initially baby planets called planetesimals, form, and then they hoover up or vacuum up the material around themselves, slowly accreting more material onto themselves and clearing out their ring of the protoplanetary disk, so that you end up with a series of, over time, planets which are all formed from the same material. And that, in this case, it happened about 5 to 4.5 billion years ago.
The lines are open. Your questions, your science-related and natural history questions to Dr. Chris Smith, the Naked Scientist, 021-446-0567. Let's go to a quick voice note.
If you tickle yourself, why is it not ticklish? Thank you, Keith.
Why can't you tickle yourself?
Let's have a go. I know I'm tickly in various places, and as Keith says, I cannot feel the tickle sensation as if someone else did that to me, no matter how hard I try. And the reason is that the brain has a particular region. It's the temporoparietal-occipital junction, where the various lobes of the brain meet, which acts as a cancellation centre. That part of the brain knows what you are doing at any moment in time, and it's also registering what information is coming back from the periphery of your body. And if one equals the other, then it pays much less attention to it. Where there's a disparity, where you get signals coming back but your brain's not expecting them, that triggers the, oh my goodness, that's the unexpected happening response, and you pay a lot more attention to it. So in essence, it's because your brain cancels out the incoming signals that it expects to get back, and this enables you not to have your attention hijacked by things that you shouldn't pay attention to. In order for us to stay alive and be safe, we need to pay attention to the unexpected, not the expected. And our nervous system is being assailed with information all the time coming from within and around our body. For instance, the clothes we're wearing, the seat we're sitting on, the shoes on our feet. And because of that, we would be continuously distracted by things that, in fact, are pretty predictable and pose no threat to us. And we would not notice the thing that's about to kill us. So what we do is to delete from what we pay attention to all the stuff we can predict is going to be there. And we pay much more attention to the stuff that we don't know is going to happen. And that includes being tickled by someone else, because you don't expect to make that movement. You don't expect it to happen the way that it's coming in. And so you do pay attention to it.
And I remember this was similar to an answer you gave a couple of weeks back, maybe a month or two back, when someone asks, Why do we like our own brand? Why aren't we as disgusted by our own farts than by other people? It's because we know it's coming from us. We know the source of it, and therefore we know what to expect. And the same could be answered for a tickle, a self tickle.
That must be the first time on this programme, and although farts crop up often on this programme, it's the first time someone's managed to link them to tickling and and calling them a sort of a flatulent tickle. Yes, I think that there is an element of that, but I think there's also an additional element, which is that we are pre-programmed psychologically to be repelled and disgusted by gross things because they pose a health risk to us. And particularly nasty smells go along with particularly threatening things. If you find, rotting organic matter, decaying corpses and stuff, we find that smell repellent and repugnant because it could infest us with the same nasty thing that turned whoever that was into the rotting corpse. So we naturally and intuitively stay away from those sorts of things. But it takes us time to learn that process. And that's why babies aren't repelled by their own feces, for example, and will quite merrily play in them until they get to a couple or 2 or 3 years old, and then they find them disgusting just like an adult. And it's that whole psychology kicking in. So I think there's a combination of factors where that's concerned.
There's a great follow-up here. It says, Naked Scientist, if I breathe in and hold my breath, I'm not affected by tickling.
I don't know why that is. I suppose it depends on where you're being tickled, because if you're being tickled round your midriff or round the ribs, which is one classic place, just under the diaphragm, if you are tensing that area, it does mean that it's much harder for the person to activate all the same sets of nerves that are being recruited to create the tickle sensation when you tickle someone. But what about if you were to do that and try tickling under your arms or something? It might mean that you don't feel the same sensation being blocked in that way. I'd have to try. Let's all try the experiment. Let's all tickle someone and then get them to hold their breath and see if that works. I think it's probably more of a psychological phenomenon. It's sort of mind over matter. I know this is coming. I'm going to tense all my muscles, make my skin taut, much harder to stimulate the nerves that I find tickly, and therefore it just diminishes the incoming sensation, and that's why it works. But, let's have a go. Everyone report back.
We'll just, speaking of reporting back, and this is why we get Ron and Kirsten off getting us ready on the open line. Have you gotten an answer yet for the rock that you found at the fossil park?
No, I haven't. Unfortunately, Cape Talkers have let us down. Also, a professor of geology at the University of Cambridge doesn't know what it is either. But then it's not his specialism. He's interested in earthquakes, another important, pertinent piece of geology this week with the issue what's going on in Haiti. But no, he's referred me to someone else who perhaps will. And I'm hoping it's not just a lump of concrete with some pebbles in it. Let's hope not. That would be very embarrassing indeed. But I did break open one of the little round blobs inside, and it doesn't look like just a piece of chert that's in there that you would normally use as gravel in concrete. So I do think it is something, but I need to find this other person who's more of a rockologist for fossils than my friend who's an earthquakeologist.
Ron has called in from Kirstenhof. Good morning, Ron. How are you?
Morning. Yes, I'm very well. Thank you very much. Chris, a quick question. How does the cloud in computer terms work? We hear about goods being stored, information being stored in the cloud. And I just wondered how and where the cloud is and who is storing it, because my phone was stolen and all the information that was on my phone was luckily stored in the cloud. Chris, can you maybe enlighten me on that?
It's going to help me as well.
The answer is, let's wind the clock back to the days of personal computers when they first burst onto the scene in the sort of late 70s, early 80s. And we got very used to storing information on a computer, but it was a computer near to us. And right through until very, very recently, that was the status quo. We would have a storage device. Initially, it was a cassette tape. Can you remember those amazing days when you would load things into computers off of cassette? Wow. And then it became the disk drive, and I've actually got in my home. I've been clearing up recently, and I found some 5.25-inch floppy disks. Amazing to think, wow. And they had the princely storage capacity of 100 K on there. Wow, it's incredible.
The kids don't know what that is.
No, and then we got these 3.5-inch floppy disks that are called floppy disks, but they're stiff, which was a bit of a misnomer, wasn't it? And then we moved into rewritable CDs and DVDs, and then hard disks really took off for the domestic market, where you could have something the size of a pack of cards that would store gigabytes and now terabytes of data. But the problem is, as has just been alluded to in this question, if something happens to that device, all of the data on it is completely corrupted, destroyed, or potentially lost forever, as many people have found out to their cost. So there's been a shift now that connectivity around the world has improved enormously, as in most people are online, most devices are online, as in on the internet, on the interconnected network, which is what internet stands for, and the connectivity is powerful. You can move big amounts of data quickly. It's become a lot more effective, safe, and therefore resilient to export that data from your local device into a distributed network of computers. So when you dial up a connection on the internet and you're talking to a computer, you're not just talking to one computer. Most of these places have got an enormous network of computers that all share out the job of talking to your computer. And it's the same with storage. There are data centers which have huge numbers of computers in them with huge amounts of storage, much of it in what we call solid state storage, where you're not storing this stuff on whirring disks anymore. This is being stored on physical memory, computer memory, which makes it incredibly fast to send and retrieve information. Stuff that's used less often does get put onto slower forms of storage, but let's focus on stuff we want quickly. So your device sends the data to a computer network somewhere, which then stores it on a huge array of computers in a redundant way, which means that it's there in multiple copies in multiple places, and those centers then share that around their network around the world as well. So your data exists in multiple places at the same time, but all synced up. And in this way, it doesn't matter where you go on Earth, with these distributed content delivery networks, you are pulling your data off of the local version of their network, where their computers have got a copy of it. And because it's always local to you, because there's multiple copies of it around the world, it's always very fast to retrieve it and you get it straight away. And because it's not on a single machine, it's all over the place. And that's why they call them clouds, because clouds are all over the place. If you lose one bit of that system, it's a bit like chopping one finger off your hand. You've still got a hand, you've still got fingers, and your hand will still work. You've just lost one of them, but you can stitch it back on by getting a copy off of another part of the network and gluing your finger back on, but it doesn't stop your hand working in the meantime. And that's what makes it very resilient, very safe, and a good place to store your treasured memories, photographs, and videos of cats.
10 minutes left to call in on 0214460567 to ask your question to Dr. Chris Smith, the Naked Scientist. And as I can predict, as happens every week at 2 minutes to 10 o'clock, we'll have 3 calls that we simply can't take. So call in now, 0214460567. Let's go to a voice note.
Just a question for the Naked Scientist. I live near the beach, and every evening, or most evenings, I go down to watch the sunset. And it fascinates me that with the sun so far away from the earth, that as it's going down, the line reflecting off the ocean gets narrower and narrower until it's only about a meter wide. And as you walk, of course, this line follows you. I kind of understand a little bit about it, but I find it hard to get my head around that. What is actually happening in the eyes to create that straight line? And then also, I've noticed on very clear days, there is a definite green flash. And I've seen it now many times. I was wondering what that actual green flash is caused by.
Chris, may I add a follow-up? I understand also that when we see the sun very close to the horizon, it's actually an optical illusion. The sun is physically actually beyond the horizon, and what we're seeing, and one of the reasons why we can look at a sunset is because the sun has already dipped, and what we see is just an optical illusion.
First of all, why do we see the sunset as this narrow strip? Well, the reason is that your eyes are a camera. And in order for you to see the sun, a ray of light is coming from the sun, and rays of light travel in straight lines through any given medium that's consistent, and they come to your eye. And when you're therefore looking at the sun, you see this disk in the sky, and the light waves that have come straight to your eye are the ones that you're making the image of the sun with. But there will be lots of other light rays that if a person standing either side of you, they would see. But the ones that you're seeing would miss them and hit the ground. So there are billions and billions and billions of light rays coming straight out of the sun. You see a straight line because you're looking at the ones that are coming straight to you. And as the sun sinks across the water, then some of the light rays will have hit the water and then reflected off of the wavelets on the surface of the water and up to your eye, again following a straight course. So when you are looking in a straight line, you are going to see the light that happens to be bouncing up off the water surface at that point. And if you were to move to the side or half a mile or whatever, you'd see another set of rays that are bounced at that angle. What you don't see, of course, are the ones that miss you and go into the hillside behind you. The green flash is part of the same phenomenon to do with actually why the sky's blue and why things look different colours at different stages of the sunrise and sunset. This is refraction. It is the bending of light as it passes through different media or media of different densities. As the sun sinks, the reason it turns red is because the light is coming at us through a thicker and thicker or greater and greater distance of atmosphere, because when the sun is directly overhead, there's the shortest distance between the outer part of the atmosphere where the light's arriving and you on the Earth's surface. But as the sun sinks, it's now coming not straight to you through that short distance, but it's coming through a bigger distance of the atmosphere, because if you think about where the sun is on the horizon, it's now got to come through a much greater distance of air. As the light goes through the air, it is going to shed some light wavelengths, because air lets through longer wavelengths that are redder colours, but it tends to interrupt or scatter bluer, shorter wavelengths. And so your eye sees the blue wavelengths coming from all over the sky, which is why it thinks the sky is blue. The sky is not blue, it just looks blue. But that means the light that's left coming straight to you is red. And that's why the sun looks more and more red as it gets closer towards the horizon. As it goes over the horizon, it does actually bend more, and this is the refraction kicking in, where you will actually split the sun's light up into a number of different colours or wavelengths, and red bends a different amount to green, and so you can separate out the sunlight into the components that are left behind as the sun has had most of the blue removed, and that means you will see sometimes on very clear days a flash of green as it finally sinks over the horizon, and that's the case. And yes, you're right, there isn't, because of this refractive effect, the sun is sinking behind the curvature of the Earth, but you're still seeing it when it's already set, as it were, because of the light being bent by the atmosphere in that way.
Excellent. David in Brackenfell, how are you doing?
Good morning, Lester. I'm fine, thank you. I would like to ask a question for the naked scientist. I came across a straight pole in part of Brackenfell Kuilsrivier, next to a pedestrian walkway, which is about 2.5 meters next to the roadway and about 30 meters from a railway line. But what I've noticed on a couple of occasions that the pole is vibrating. And it is, you can see it with your eye. If you're close enough to it, standing next to it, you can see it with your eye. And if you put your hand against it, you can feel the vibration of the, yes. But next to that sign or the pole, there is a couple of other signboards also. But I've touched those, and those are not vibrating. Yes.
Excellent.
So I would like to know what is the possibility of that.
Chris?
I think what's going on here is that you have discovered something which is tuned into the resonant frequency of that particular patch of roadway. That's one possibility. What do I mean by resonant frequency? Everything that we have around us wants to vibrate at a certain rate. And if you think about a pendulum swinging, if you just pull a pendulum back and let it go, depending upon how long the shaft is on the pendulum, it will swing backwards and forwards at a certain rate. A swing that a child is sitting on will swing backwards and forwards at an ideal rate, and you can make that bigger by pushing it harder, but it'll swing backwards and forwards at a certain rate. When you're driving your car down the road, you'll notice at certain speeds the dashboard shakes and vibrates. That is the sweet spot, the resonant frequency for that thing. Now that pole is embedded in the ground and then projects up above the ground and has therefore a certain length and mass and therefore a certain resonant frequency. And anything that vibrates it, traffic going past on the road, the railway line nearby, is going to add energy to that pole and make it vibrate. And it will therefore build up momentum inside the pole and vibrate at its resonant frequency. That might be what you're feeling. On the other hand, it's also possible that that pole has got something electrical attached to it, perhaps a big transformer or something, perhaps underground. And transformers also vibrate because they are converting mains electricity, which is probably at 50 hertz, in other words, 50 cycles a second, from one voltage to another. And that means that there's a magnetic field going backwards and forwards inside the transformer at about that rate. And that will make the armature of the coil vibrate at about that rate. And this will be transmitted to the box that the transformer's in, and therefore anything that it's stuck onto. So you may also be feeling a mains hum. It could be that too. So those would be my two speculations as to why this random pole that you're feeling in the street is vibrating.
And that's it. As predicted, Chris, it's about 2 or 3 calls here that we have to let go because everyone waits for the final 5 minutes of The Naked Scientist. We'll try and do this again.
It's like an auction, an online auction, isn't it? Everyone always waits for the best bit at the end and then piles in. Can I be that person who just sneaks in at the end with that winning bid?
Exactly.
Not this time.
But hopefully next week we'll have our school kids on air with us.
Oh, I hope so.
We're going
That'll
to
be
get
good.
confirmation with them from early next week. But Dr. Chris Smith, The Naked Scientist, have a great week.
And you, Lester. Bye, everybody. Bye-bye.